Right. So I welcome you all to the last day of the workshop, and today we are going to discuss about the remaining part of the section that we started last time, the machine learning, the introduction to machine learning part, and also we have to implement few algorithms here, train a machine learning algorithm and get some results today. And before going on to the practical implementation, we need to uh, finish the theory part, the finish what we started yesterday, and we will simply I will simply then we will go into implementations, right? Okay. Uh, Unfortunately, it's not allowed. The personal recording is not allowed. Sorry for that. It's actually is not allowed. Okay. So. Right. So last time, this is what we actually discussed at the end, and also we discussed about at the beginning what's machine learning and what is artificial intelligence and deep learning. So we discussed about these things, and we got to know the differences between these three categories and what are the similarities and also the dissimilarities, right? So you know what machine learning and you know what deep learning. But anyway, when it comes to machine learning is simply about compute algorithms, and they are like trainable algorithms, and they can be trained for a specific task. So that's what you simply mean by a compute algorithm, a trainable algorithm. And the most important thing here is that the ability of the attribute, like it's trainable, right? So that's the most important thing. Machine learning algorithms are trainable algorithms, so you can train it for a specific task. So this is similar to our intelligence. So this is similar to our as I mentioned last time, this is similar to our intelligence. So if you have a new task like learning French, right? So your intelligence can be trained for that, right? So similar thing, machine learning algorithms also can be trained for a specific task. So that's what we discussed last time, and we also discussed what deep learning is also about, right? And there are three main categories under machine learning: supervised machine learning, unsupervised machine learning, and reinforcement learning. So what we are discussing today is what we are going to discuss today is supervised machine learning, right? So we will go into the detail about supervised machine learning, and we get to know about what the model, the supervised machine learning model, and we will apply a simple application as well. But in this workshop, we are not going to discuss about unsupervised machine learning or reinforcement learning, right? Therefore, what I'm going to do, I will simply explain you the differences between supervised and unsupervised and reinforcement, right? So we'll discuss about the differences and the similarities and what it means by supervised, unsupervised, reinforcement learning, and then get to know a brief idea about those three categories. But we will in detail discuss about supervised machine learning model, right? So I'm not going to get a machine learning example, but I will get a real world example, and I will explain what supervised, unsupervised, and reinforcement is about, right? So when it comes to supervised, so let's take a common example. Now, let's say that you want to learn swimming, right? You want to learn swimming. And if you are going to do it in a supervised manner, or if you are going to do it like under supervised category, then it's like, okay, you are going to hire a instructor, a swimming instructor, right? And simply you are going to follow the instructions given by him and learn to swim, right? So supervise, as the name suggests, you are going to learn something under the supervision, right? You are not learning it by yourself, or it's not self-learning. You are going to like train on something by I mean by some by referring to one some others experience, right? So we are going to get some others experience. Okay, we are going to get a supervised an instructor, and we are going to learn according to him, right? So the idea here is that we are going to like based on some others experience, and we are going to learn something. It's not self-learning kind of a thing, but still you are going to learn something, but you are going to like based on some others experience, past experience, you are going to train something, right? So that kind of a similar idea is there. And when it comes to unsupervised learning, no, in unsupervised learning, you are not going to get the help of an instructor, but you are going to learn swimming by yourself in the sense you don't have any instructions, you don't have any supervisor, you don't have anything, but you try yourself, right? And you'll follow a book, you'll see some videos, let's say, but still you are going to do some training, right? You are going to do some training, but no any supervision here, right? So that kind of a thing is unsupervised machine learning. And when it comes to reinforcement learning is the most interesting thing here, right? So if we want to learn swimming and you are going to do it in the like the reinforcement learning manner, right? It's like if you want to swim, like you will be uh, taken to mid. I mean, you will like you are going to go to the middle of the sea, right? And you are going to jump off to the sea simply, right? Or you will be dropped off in the middle of the sea, right? So imagine that kind of a situation. Now this is not a swimming pool. This is a, I mean, the middle of the sea, right? Right. So there are a few, I mean, 20, 30, or like that, like let's say 100 feet, right? Depth, and what you have to do there. So you have only two options simply, right? So you have two options, do or die, right? So very simple, a binary solution will be there, do or die, right? So you better try, right? Without giving it up. So what you can do is what you're going to do, you will try different movements, and you will try different things, and somehow you are going to like do trial and error. Let's say that if you don't, if you are not, if you don't know anything about swimming, but anyway you will try something, right? So you are going to do things trial and error, in trial and error manner. So that's what reinforcement learning is actually. So you are going to do several things, and you are going to anyway learn yourself there, right? So online in the sense like you are going to learn in the scene, right? So you are going to learn in the real application, no prior training, but you are going to train in the real application, right? So you are going to do lots of actions, lots of movements. You are going to try different movements and see whether you can go up, right? Go up, and right. So when you are going to do something, and if you are going down, then you know that this action or this movement is not going to work, so you are going to try another, right? So likewise you are going to learn something at uh, the environment, right? At the real environment, not a prior training. It's like in scene training, right? So that's what you call similar reinforcement learning. But I'm not going to go into detail about unsupervised or reinforcement, but this is what actually you are going to find in these three. So we have different algorithms in each category. In supervised machine learning, we have lots of like support vector machine, K-nearest neighbor, linear regression, Gaussian naive Bayes, right? We have lots of algorithms available under supervised machine learning. So machine learning is about algorithms. So supervised machine learning, we have a different set of algorithms. When you are going to go into unsupervised learning, you have K-means clustering, mean shift clustering, principal component analysis, hierarchical clustering, right? So likewise, we have lots of algorithms under unsupervised machine learning. If you go to reinforcement learning, Q-learning, right? SASA, dynamic programming, right? TD lambda. Likewise, we have lots of algorithms available under reinforcement learning. So in these three categories, we are going to find different algorithms, right? So that's what simply it's about. So simply machine learning, we can divide it to three main categories like this. Got it? Right. So now we are going to focus about supervised machine learning model, right? So we are going to like keep the unsupervised and reinforcement learning away, and we are going to discuss about in detail. We are going to discuss about the supervised machine learning algorithm or supervised machine learning model. So this is what we are going to see, or this is what we are going to actually learn as supervised machine learning, right? So in order to understand this model, right? In order to understand this model, uh, a very simple concept now. This is the model of supervised machine learning, right? So if you want to, if you want to solve something, right? If you want to solve something using supervised machine learning, first you have to convert your problem into this kind of a format, or you have to apply your problem into this form, right? So that's what you call supervised machine learning simply, right? So now we will discuss about this in detail. So this is the supervised learning model, right? So now you can see this the blue color box. So this is the algorithm, right? This is a general algorithm, but you can substitute like, okay, k nearest neighbor, support vector machine, any algorithm. But I wanted to say, okay, this is generally a supervised machine learning algorithm, right? A general supervised machine learning algorithm is represented by this blue color uh, box, right? So I will explain you this model using a real world application, right? So let's say that you have exam, right? So you have exam coming on like let's say 6 months, right? So you have zero knowledge on that subject. So you have a particular subject and there will be exam coming on like 6 months and you have zero knowledge, right? So let's assume that this blue color box, right? This blue color box is your brain, right? So we are going to assume that this blue color box is your brain, right? We are going to assume that this is your brain, right? And let's assume that this exam, you can gain knowledge, right? You can gain knowledge or gain experience to write this exam by just by doing past papers, right? Let's assume now all the exams are not like that, but let's assume this exam you can get knowledge by just doing some past papers, right? So what you are going to do, first you have to train the algorithm, right? So you have to train your brain first before going on to the exam. You have to learn yourself. You have to train your brain into this algorithm. I mean, sorry, brain into this application, right? So you are going to get two things now. First, you have to do training. Here you can see training. Training is done at the first place. Training. So when you are doing training, you have to do it using two things, right? So those are called features and labels. These are called features and labels, right? So first you have to train now. Before going into exam, you have to learn yourself, right? So that's what you mean by training. So the features are simply in this case like questions and labels are just like answers, right? So what you are going to do, your brain, this blue color box, right, will be trained from the past papers like questions, answers, right? So you are going to work out like, let's say 10,000 questions and answers, right? So questions, answers, questions, answers. So you are going to work out yourself, right? And when you are going to like do 10,000 questions and answers, right? 10,000 questions and answers, what happens actually, right? What happens? You are going to identify the relationship between questions and answers, right? We are going to find the relationship between questions and answers. So for this question, this is the answer. This question, this is the answer. This question, this is the answer. Likewise, you are going to like explore 10,000, let's say 10,000 questions, right? So we are going to, that's how we are going to get the knowledge now. In this example, the knowledge will be something like, okay, for this kind of a question, this is the answer. So that means you are going to identify a relationship between question and answers, right? You are going to identify relationship between questions and answers. So that's what happens when you are going to like provide more and more question and answers here, right? Okay, let's say you are going to train your brain. So what happens when you are going to explore lots of question and answers, your brain will be trained on those question and answers, right? After the question is done, So the testing comes, right? The testing. So in the testing, what you are going to do? In the testing, what you are going to do? Can you see? You are going to get questions in the exam, right? After training, in the exam, what happens? You are going to get questions, right? Got it? And you are going to get questions. Are you going to get answers in the exam? No, right? You are only getting questions. That means you are getting features. Now, what your brain does here, so you have experience, you have a knowledge. What's the knowledge? That you have done like 10,000 past papers. So you have the knowledge, right? So then the new set of questions are given. So you have earlier, you have identified a relationship between question and answers. So what now you can do? Okay, so you can get these questions, let me say Q dash, and you can provide some answers, right? How we are going to do that? You are going to get set of questions in the exam. So based on your past experience, the past knowledge that you have gained, you are going to provide some answers. So these answers are like predicted answers, isn't it? So we can't say that, okay, so the predicted, I mean, the answers that you are going to provide for an exam, like if they are 100% correct, right? So you are going to get 100% marks, right? But that's not the real case. So in the real case, what you are going to get is, what you are going to provide is some predicted answers. You can't say that the answers are like perfect. But for these questions, you are going to provide some predicted answers. So that's what we are going to do in simply here, right? Got it? So we have to have a method of evaluating these answers, right? So before going, I mean, I said this, but before going on to a real exam, you have some term tests, right? So some quizzes before going on to the real exam, right? So likewise, before going on to the real exam, you have to like provide some answer known questions, right? So you have to provide some answer known questions, and you have to get the answers provided by yourself, right? Then you have to compare the answers provided by you, the predicted answers and the real answers. Then only you can evaluate yourself. So you can get a score like, okay, 85, 90. Then you say, okay, I'm good and I'm fit for this exam. But if you are getting like, before going to real exam, if you have a quiz, if you are getting like 35 answers, no, that you are not ready to the exam, right? So before going on to the real world predictions, you have to evaluate the model yourself. That's one of the important things when it comes to machine learning. Anyway, this is how it's happened, right? This is how it happens, right? So now you can you have a basic understanding about features and labels. Okay, these are the features and these are the labels. Okay, so first training is done using features and labels. So then the relationship between the features and labels will be identified. Once the relationship will be identified, that means after the training is done, you can provide some features and you can get some labels, right? Got it? So that's what it is about, right? So now we got a real world example, but this is not going to work all the time. So now we will go to the general definition of features and labels, right? So before applying machine learning into some application, right? Before applying machine learning into some application, the most important thing that you have to do, or you have to have, is that you have to have a problem, right? You have to have a problem. Understood? So before applying machine learning, you have to have a problem to apply machine learning, right? Understood? Otherwise, like knowing machine learning and having knowledge on machine learning, no, that won't do anything. You have to have a problem, then only you can apply a machine learning algorithm and get results, right? So the most important thing, in order to train a machine learning algorithm, first you have to have a problem, right? So let's say I want to predict stock market values. Then there's a problem. I want to like build a self-driving car. There's a problem. Likewise, you have to always have a problem. But for the simplicity, I'm not going to go into a complicated problem here, but I will take a very small problem, okay, predicting whether it's going to rain today or not, right? So what I want to do here, I'm going to get a simple problem, a problem definition. I'm going to define my problem here, and then I'm trying to apply machine learning in order to solve this problem, right? So that's the objective. I have a problem definition, and I'm trying to apply machine learning in order to solve this problem, right? So it will be predicting whether it's going to rain today or not, right? So when it comes to a problem, okay, done. The first step is done. Let's assume that the first step is done. So you know, okay, you have a problem. Simply you have a problem. Then the next thing, you have to apply this model, supervised learning model, right? Supervised learning model. But before applying the supervised learning model, in order to apply supervised learning model, you have to identify two main things like the features and labels. The features and labels of this problem, right? First, to have you should have a question, or should have a problem. Then from that problem, you have to define the features and labels, right? So it's a bit straightforward method, right? So you have to identify features and labels of this problem. So the most easiest things to do is identifying the label. So we will do that first, right? So labels will be simply the possible outcomes of the problem, right? The labels will be the possible outcomes of your problem, right? The possible outcomes or the solutions for your problem. So if it is going to rain today or not, that's the problem definition. So what are the outcomes, the possible outcomes of the problem? Any idea? So our problem is whether it's going to rain today or not. So what are the possible outcomes of this problem? That will be the labels. Quickly. No, the logistic regression won't be done today, but we will do the Knearest neighbor algorithm. Right? Yeah, 0, 1 simply. Right? 0, 1. So what do you mean by 0, 1? Rain, no rain. So two possibilities are there, right? So those will be the labels, 0 and 1, right? 0 and 1. Got it? It's a binary problem. Yes, exactly. But all the times the problems won't be binary, right? All the times the problems won't be binary. We have like several outcomes. All the times problems are not binary, but I will explain. But anyway, here it's binary, like rain or no rain. Right? Rain or no rain. We will get this simple example. Then the next thing is to define features. Labels are done. So what's the important thing when it comes to labels? The problem itself, the problem definition itself provide you the labels, right? The problem definition itself provide you the labels. Understood? So if you have a problem, the labels are defined already, right? But the features are not like that. So what do you mean by features? Features are the critical attributes that the labels are dependent on. Critical attributes or the factors that the labels are dependent on. What do you mean by that? Okay, so labels are rain or no rain. Rain or no rain. So what are the factors that decide whether it's going to rain today or not? Any example? Few examples. Yes, quickly. Yes, quickly. Yeah, exactly. Humidity, temperature, wind speed, light intensity, right? Not one factor, but you can get several factors, right? So features are the critical factors that the labels, factors or the attributes that the labels are dependent on. So once you have a label, right? Once you have a label, you have to define the features, right? So you have to like do some now here. you should understand that this is domain based, right? Got it? Understood. So in this one, it's based on, like, you have to have a domain based knowledge, right? Domain knowledge simply, right? I mean, for this example, it's not that much necessary, but if you take a example like what, let's say, let's say predicting heart risk level, right? Predicting the risk level of having a heart disease, right? Predicting the risk level of having a heart disease. So the features, what are the features? What will be the features? Gender, age, right? Cholesterol level, diabetics or not, right? Diabetic patient or not. So now the thing is that the application that you are going to solve, sometimes you can't define features yourself. Why? You need the domain knowledge. You need a specialist knowledge on that. Most, like, for example, when it comes to like something related to health, right? Right, health and medicine, you have to have domain knowledge, right? So you can't define features yourself. So you have like either refer some research papers, or either refer, you have like contact a resource personnel, right? So if you are in like a health domain problem, uh, you have to refer to a doctor likewise, right? So defining features is not straightforward. You need to know the, I mean, you have to have, sometimes you have to have the domain knowledge, right? So how to solve a machine, how to learn a problem in machine learning? Simply, first you have to identify the features. First of all, you have to have a problem. Once you have a problem, from the problem you have to identify features and labels. So identifying labels is straightforward thing, and identifying features, like the critical attributes, you have to find the critical attributes that the labels are dependent on, right? Then what you are going to do, you are going to create a data set. Now, creating a data set, uh, it's not, it doesn't mean, right? It doesn't mean that you have to create a data set like assuming the values. No, you have to get a historical data set. Historical data set in the sense like a real data set. You have to get a real data set, right? Right. So you have to get a real data set from past data or past experience. For example, like let's say that we are going to go into like last 5 years, right? Last 5 years, and for each day we are going to get the, okay, so this refers one day, right? A single day. Okay, temperature of that day, humidity of that day, wind speed, the, like let's say the average values of the temperature, humidity, wind speed, and light intensity, and the label, whether it's a rainy day or no. Then the second day, right? So likewise, we have to get some past data here, right? We have to get some past data, and these should be historical data. That means real data, already existing data. Got it? So you have like get features and labels from that data set. Understood? So this data set should be real and like past papers, right? Question and answer. So they are already existing and historical questions, and I mean historical data set kind of, right? Understood? So once the next step is to have the data set. So the data set defining, you can't define your data set randomly. No, you can't do that. You have to have a real data set. That means historical data should be there in the data set. So once that requirement is satisfied, then you can take a machine learning algorithm and then you can train it, right? What you have to do is you have to provide the features here, features and labels. Then you can train the machine learning algorithm, right? So after training is done, what you can do, right? What you can then do, you can get predictions, right? How? you are going to apply today's data. What do you mean by today's data? Today's temperature, today's humidity, today's wind speed, today's light intensity, right? The average temperature, humidity, wind speed, light intensity of today, right? You are going to apply it to the machine learning algorithm, and machine learning algorithm. So this is features, right? So we are going to apply features. These are features. So when we apply this, the machine learning algorithm now provides you a label. It's going to predict whether it's going to rain or not, right? That's what simply machine learning, that's how it works. Supervised machine learning model, this is how it works, right? So you are going to train on questions and answers both, but at predictions, when you are going to give predictions, you get questions, and based on the past experience, you are going to provide answers. Similar here, you are going to provide some like last 5 years temperature, humidity, wind speed, light intensity, and whether it's a rainy day or not. And after training it, so when you get a new features, right? Only features, it's capable of giving prediction. So how the prediction is given based on the past data, right? Based on the knowledge that they have given, right? So don't get the idea wrong here, right? So if we apply a new data, don't think that this data should be existing in the trained data. No, right? So when you are going to go to the exam, you are not going to get the same question which was in a past paper, right? No, you are not going to get the same, but you will get different questions. I mean unseen questions. So unseen data you are going to get. So when you are going to get unseen data, you are going to perform an approximation. How? Okay, you are getting a new question. You haven't seen this question earlier, but based on the past experience, you are going to provide the approximation. So you are going to think, okay, I have seen this kind of questions earlier. So answers for those questions, answers for this. So I also provide the answer like this. That kind of a thing is done. Understood? So that's the approximation. So the new data should be predicted, the new set of features that you are going to predict it, not needed to be a seen, it should be unseen data, right? For unseen data also, machine learning algorithms can provide predictions, right? So what machine learning simply does, right? When you are going to provide some features and labels, so the machine learning algorithm, we are going to provide like lots of data, like 10,000, 20,000, 100,000, right? So we are going to, like, if you are doing machine learning, you have to have data sets. You have to have data. That's the most important thing. Especially for supervised and unsupervised machine learning, you have to have data sets, right? And they should be large data sets like 1,000, 10,000, depend on the application, 20,000, sometimes 100,000, sometimes millions of data needed, right? Once you have the data, you can train it. And after training it, what happens? It's going to identify the relationship between features and labels. So after identifying the relationship between features and labels, when a new feature, unseen feature is provided, unseen question is provided, the machine learning algorithm is going to provide the approximation. Okay, I have this kind of a similar, I have seen this kind of a similar question earlier. So the answer for that question was this. So I assume that the answer for this question also should be the same, likewise. Got it? Okay. So the next thing, when you are going to deal with machine learning, first, when you have a problem, now you know, in order to train a machine learning algorithm, you have to have a problem, right? When you have a problem, right? When you have a problem, first you have to identify that problem type. What's the problem type? So in machine learning, especially in supervised type machine learning, when it comes to supervised type machine learning, we have two main types of questions called classification problems and regression problems, right? Classification problems and regression problems. So what do you mean by classification and regression? So once a problem is defined, so when you have a problem definition, and if you think that you want to apply machine learning to solve this problem, right? First of all, you have to identify the type of that problem, whether it's a classification problem or a regression problem, right? Whether it's a classification problem or a regression problem. right? So how we are going to do that? You have to refer to the label. So we are going to refer to the label, and we can then define whether this is a classification or regression problem. So what I mean by a classification problem? If your problem, in your problem, if the labels are classes or categories, then it's called a classification problem. What it means? Rain or no rain, right? Got it? Then um, um, what are the problems? Okay, the stock market value, let's say, stock market value, whether the stock market value goes up, go down, or remain the same. So three possibilities are there, right? So what are the other classification problems? Can you remember that the question I told you, like this one? So we are going to provide the X-ray image to a algorithm, and the algorithm going to predict whether this is a COVID-19 positive patient or a COVID-19 negative patient, right? Got it? That's a classification problem. Understood? Yeah, credit card fraud, exactly, right? So likewise, so if your label is a class, now don't think that always it should be a binary problem. No, that's why I told you, like, okay, go up, go down, or remain the same. Right? Go up, go down, or remain the same. So three possibilities can be there. Now, yeah, I'll then discuss about, I will discuss in detail about classification, but I will discuss about regression as well now, right? I know, like, provide you the difference. So regression problems, the other type. The regression problems are when regression problems define when your label is a number. For example, if you want to predict the rainfall in millimeters, right? If you want to predict the rainfall in millimeters, so it's a number, it's not a class, right? It's not like rain or not. It's a class. What I mean by class? It's rain or no rain, right? But predicting rainfall in millimeters, no, it's not a class. It's a number. It can be from 0 to whatever the number, right? It can be from 0 to whatever the number. Risk of having a heart disease, right? Risk of having a heart disease, so 0 to 100, right? 0 to 100, 0% to 100%. So the label can be anything, right? Isn't it? Why? So are there like 100 classes between 0 and 100? No, you can't say it like this, right? So if I say, okay, risk of having a heart disease from 0% to 100%. So you can think, okay, then there are 100 classes: 0 class, first class, second class, 99 class, like 100 class. No, it can be anything. Like it can be 36.8.95, right? Sorry, 36.859, or it can be 50.2. It can be 78.856. It can be any number. It's a continuous number, right? So the risk level is a continuous number. It can be anything, right? The stock value of a particular stock, not goes up, goes down, or remains the same. But if you want to predict a stock market value of market tomorrow, the stock market value of tomorrow for a particular stock, what we have to do? It's a regression program, since it can be anything, right? Any number in between, some range, right? So if your label is a class or a category, if you are going to predict a category or a class, rain or no rain, stock market value go up, go down, or remain the same. So three possibilities. Likewise, when it comes to regression problem is simply a number. Rainfall in millimeters, right? The risk of having a heart disease, likewise, right? So let me show you an example. Can you tell me whether this is a classification problem or a regression problem? Give me a second here. Right, so not this one. Yeah. Okay. Right, so give me a second. I will. This one, I think. Okay. Right. So I have this kind of a small writing pad, like a canvas, right? So listen carefully. I'm going to write a single digit here, only a single digit, not multiple digits, right? I'm going to write a single digit here, right? And I have a machine learning algorithm which can predict what this digit is, right? So simply then what's the task of the machine learning algorithm? Whatever the digit, a single digit, you are going to write in this space, the machine learning algorithm needs to predict what that digit is, right? So is it a classification problem or a regression problem? Yes, okay, good. Classification. Others, what do you think? Yes, what do you think? Quickly. Yes, exactly. So this is a classification problem, right? Why? How many labels are there? How many possible labels are there? Yes. How many possible labels are there? Yes, quickly. How many possible labels are there? The next question. How many possible labels are there? No. How many possible labels are there? Okay, for this problem, how many possible solutions are there? Then that's what you mean by label, right? For this problem, how many possible solutions are there? When you write a digit, how many possibilities are there to that digit to be? Yes? 10, exactly, right? 10, right? Now, whatever the digit that you are going to write here, there will be 10 possibilities. It can be either 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 10 labels. Whatever the number you are going to write here, right? Whatever the number you are going to write here, there are only 10 possibilities. Either it can be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 10 possibilities, isn't it? Right? Right, good. Right. So I think now you understood, right, what it is about, right? So if you predict the stock price, right? So these are some examples. So in self-driving cars, the features will be the pixel values of the image captured from the camera attached in front of the car. Each and every individual pixel. So the NVIDIA self-driving car I showed you yesterday, it used 66 to 220. This is the resolution of the images that they are using, right? So they take all the pixel values of that image as features, and the label will be the steering angle. So it's going to map the image captured from the camera into a steering angle, right? The image captured from the camera into a steering angle. Understood? So then stock market value predictions. So usually what we are going to do, so if we want to predict the tomorrow stock value, right? Tomorrow stock value, what we do, the input will be last 50 days stock price as a time series data. Not always 50, but it can be 10, 20, 50, 60, 100. But anyway, last 50 days stock price, for example, right? So we are going to get 50 features then, 50 features. Last 50 days stock price. And the prediction will be tomorrow's stock price, right? So COVID-19 prediction using X-ray images. So you are going to get the X-ray image. So features of this image, right? The features will be the pixels of this image, and the label is a classification label, right? So this is a regression problem. Since you are going to predict a price, it's a number. So this is also a regression problem, isn't it? The steering angle, right? Right? And COVID-19 positive or negative, it's a classification, right? Classification problem. Right? So object detection APIs, can you remember the object detection API I showed you last time? Right? So object detection APIs, any idea? Is it a classification kind of a problem or regression kind of a problem? Object detection APIs. Can you remember that the video I showed you last time, that James Bond film, the object detection? Yes? Yes, exactly, classification. Why? Usually it has like 100, 200 objects it can detect. Cats, dogs, rabbits, likewise. It's not a regression, right? It's going to predict, okay, whether this is a cat, dog, rabbit. It has some fixed amount of classes it can predict, right? Then the risk of having heart disease, age, gender, TCL, HDL, smoking. So these are like the features. Age, gender, total cholesterol level, high density lipid, smoking or not, diabetics or not. Then the label will be the risk of having heart disease. Yeah, all of them are classes. Yes, exactly. So the important thing, when you have a problem, first you have to solve it. I mean, before solving it, what you are going to do, you have, like, before applying machine learning algorithms, yes, you have to identify features and labels, but you have to first define whether this is a classification problem or a regression problem. Since the algorithms, the pre-processing methods, the theories that we are going to apply, right, will be different, right, to each other based on whether it's a classification problem or regression problem, right? For classification problems, we apply different algorithms, different theories, and different pre-processing methods and everything. For regression problems, we have different set of algorithms and different set of things, and different algorithms and different pre-processing methods. Understood? Right. So you have to keep that thing in your mind. Right? You have to keep that thing in your mind. Understood? Okay. Right. So first analyze whether it's a classification problem or regression problem. Then you can decide, okay, what you are going to like apply and how to define features and labels. Data set collection, that can be done later, but first you have to analyze the problem, whether it's the classification problem or a regression problem. Understood? Once it is done, right, you have to select the algorithm, right? You have to select the algorithm. What I mean by algorithm, that I told you at the first phase, machine learning is about algorithms, right? Machine learning is about algorithms. So that means we have lots of algorithms available, right? We have lots of algorithms available. And the thing here, like, let's say supervised problem. Okay, your problem is a supervised problem, and your problem is a classification problem, and you are going, like, it's a supervised learning problem, let's say. Then you have few choices here. You can apply either support vector machine, nearest neighbor, decision tree, Gaussian naive Bayes, logistic regression, uh, uh, what are the other classification algorithm, decision trees, Gaussian naive Bayes, naive Bayes, then logistic regression. Uh, Likewise, we have lots of things. I haven't mentioned all of them here, right? Those are few. We have like uh, several solutions, several algorithms that you can use for classification problems and supervised type classification problems, right? And the other thing, for example, now, okay, I will come to that point later. So if your problem is a regression problem, right? If your problem is a regression problem, you can apply linear regression, you can apply support vector machines, you can apply random forest regression. Hold on. Now, a support vector machine, was there in the classification? Yes. Support vector machine has both versions, like it can be used, like there are two versions, the classification version and regression version. So you have two versions of support vector machine, right? So if your problem is a unsupervised learning problem, and let's say it's a classification problem, then there are lots of applications like k-means clustering, mean shift clustering, Gaussian mixture models, spectral clustering. And if your problem is a dimensional reduction algorithm, dimensional reduction problem, that's also categorized under unsupervised learning. Dimension reduction algorithms are also categorized under unsupervised learning. Then you can use manifold learning or principal component analysis. Now I know that you are confused here. What are these names? So what are the differences? The thing is, if I want to predict whether it's going to rain today or not, what you have to do, first you have to identify whether it's a classification problem or a regression problem, right? When it is done, if you are now okay, whether it's going to rain today or not is classification problem, then you can apply one of the algorithms available here, any one of the algorithm available here, any of the algorithm available here. And don't think that these are the only algorithms available. No, I have listed a few here. There are some other algorithms as well, but I have listed here the most important and the most famous algorithms under each topic, each category, right? So your problem, let's say your problem is whether it's going to rain today or not, you can use any of the algorithm available here. Then okay, so then if we can use anyone, why you have several options here? What's the difference between? Yes, the thing is, now I said that you can apply any algorithm to solve your problem, okay, whether it's going to rain today or not problem. But I didn't say like it's going to perform this, all the algorithms are going to perform as the same. No. Support vector machine may perform in a different method, right? The only difference is that their working principles are different. Support vector machine works with a different working principle. K-nearest neighbor is working with a different working principle. Decision tree is working with a uh, different working principle, right? Understood? Got it? Yes. So yeah. So therefore, uh, what I wanted to highlight here is that now we have lots of options, but I'm not saying that all the algorithms are working similar, right? Or as the same. For example, now if you take a class, right? If you take a class, in that class there will be like, okay, there will be always one. There will be there will be one first of the class, right? First of the class. But the first of the class, like its overall maximum mark. If you are going to take overall maximum mark, he or she has the maximum mark, right? But for different subjects, right? For maths, someone may take the highest marks. For English, some other one may take the maximum mark, right? For math, some other one take the maximum mark. But overall, there is a well performer, I mean the best or the first in the class, right? So my point here that these algorithms, like I can't say, okay, support vector machine is good for rain and no rain detection. Nearest neighbor is good for handwritten digit recognition. Decision tree is good for image recognition. No, I can't say it like that. But we have lots of options. Then you may be wondering, okay, how we are going to select the best for our application. It's application dependent. So we have two methods. So the question is, okay, if your problem is a classification problem, you have several options. You have several options to select which algorithm to apply, right? How to select this? You have two main methods. The first one is you can see the past. See the past in the sense you can read the research papers or the previous done works of the others and see, okay, for rain and no rain problem, what are the algorithms they have used previously? And you can, based on that, you can select that one. Or else, when it comes to coding, when it comes to practical coding, you have to, I mean, if you want to change the algorithm that you are going to apply for this problem, if you want to change the algorithm that you are going to machine learning algorithm that you are going to apply for this problem, you have to change only 2 lines. You have to change only 2 lines of code, right? Only 2 lines. So therefore you can change. You can first apply support vector machine and see how it performs, and then you can apply Knearest neighbor and see how it performs, and you can apply decision tree and see how it happens likewise. Understood, right? So that's how we are going to do. But for different applications, we have different options here. So how to select the best? As I mentioned, you can apply all and see which gives the best, or else you can see the past, what they have done, and they may have, okay, they say, okay, for face recognition, support vector machine is good. Likewise, you can select from that, or else you can try different algorithms. It's matter of changing 2 lines in the code and see which gives you the best results, right? Okay, so these are algorithms. Now there are lots of algorithms and comes under machine learning. For different categories, we have different machine learning algorithms, right? But anyway, we are not going to talk about all, but we will discuss about one of the simplest algorithms that you can understand, K-nearest neighbor algorithm or the nearest neighbor algorithm. Now don't think, though I said this is simple algorithm, don't think that this is like not performing well, right? Don't think that it's not going to perform well. No, it performs well. But the thing is, the working principle or the theory behind the K-nearest neighbor algorithm is quite simple, right? Understood. So that's why I'm going to discuss K-nearest neighbor, since as beginners, it's quite easy to understand the K-nearest neighbor algorithm. So why we have different algorithms? The working principle, the theory behind all the algorithms are different to each other. So the method or the working principle that the nearest neighbor use is different to the working principle, the math behind support vector machine, right? And also their results, that for the same problem, these algorithms will give different results, right? I can't say support vector machine is the best. No, nearest neighbor is best, good for some applications. Support vector machine is good for some applications. So you can't directly say that. So what's the only option you have? You can change those algorithms and see for your application which gives you the best results, right? Okay. Right. So now what we are going to do, we will now move on to a practical application, and we will see how we can code, right? How we can code, right? Okay. So this problem is a very common problem, and this known as the hello world of machine learning, right? So now we know that we have only learned about the supervised machine learning. You don't know anything about unsupervised or reinforcement. We are familiar only with supervised type machine learning, right? But what we are going to do here, is get a simple example, right? A sample, right? And what we are going to do here is to analyze this problem, right? And apply the things that we have learned up to now. The concept that we have learned up now, we are going to apply them here, right? So that's why we have we are going to consider this problem, right? Okay, so the problem is iris flower example. I mean, there's no any use of doing this example, but to get familiarized with the things that we have learned up to now, I'm doing this, right? So that's the only purpose of doing this. So what mean by the iris flower example? This is known as the hello world problem. Like, in order to understand the basics, in order to as a beginner, so this problem is recommended, right? So what mean by the iris flower example? So this problem was arised in 1936, right? 1936. And this was addressed by British statistician and biologist Ronald Fisher in 1936, right? So we have a question, let's see. The rain or not rain problem. No. We are not going to discuss about the rain or no rain problem, but we will do a better example. This is a better example than that, right? Okay, so this problem, what's the problem? That there is a flower, not in our countries, but let's say in British, right? There's a there are a set of flowers called the iris flower, right? So iris family has three main flowers, right? Iris family has three main flowers called iris versicolor, iris setosa, and iris virginica, right? So the thing here is that they looks the same, right? The biologist, the interested person, they can identify the difference, but we the general people, like, we can see like these are quite similar to each other, right? So what Ronald Fisher wanted to do, Ronald Fisher wanted to identify some features, and he wanted to like build a mathematical model using statistics, right? Not machine learning, but 1936, no, machine learning was not there. The concept machine learning was not there, but using some statistical method, the Ronald Fisher wanted to solve this problem. I mean, he wanted to build a method in order to like identify these three flowers separately using a mathematical model in a mathematical a method, right? So here three flowers, versicolor, setosa, and virginica. So if you want to apply, like, okay, let's apply machine learning for this, the supervised machine learning, and let's say that we are going to train this algorithm. And so we are going to train this algorithm, for example, a Knearest neighbor algorithm. And after training that algorithm, we are going to like, okay, we are going to build a machine learning algorithm which can identify these three flowers separately, right? So first, now if you use machine learning, we will go step by step. But if you want to solve this problem, identifying these three flowers separately, first of all, tell me whether it's a classification problem or regression problem before going on to anything. Yes? Exactly, it's a classification problem. So how many labels are there? How many labels are there? How many labels are there? Three. Setosa, virginica, versicolor. So can someone identify, okay, then the critical thing, right? Finding labels is quite straightforward, right? So the labels are dependent on the problem definition, right? So if you want to identify these three colors, those three colors will be the labels, right? But then the most critical thing to do, not straightforward. So then can you identify the features of this problem. Tell me some examples. Quickly. Shape. Okay. Can't we get the color? Why can't we get the color as a feature? Color? Can't we? Color? Why can't we get the color as a feature? Yes. Why? The same color, right? The same color. Why the same color? Can't we get the weight? Weight. The size, the radius, no, all of them are like quite the same, right? I mean, I can't say about exactly about the weight, but other things, color, size, and everything, like they are the same, right? So if you don't have these labels here, if you don't have these labels here, you can't even, like, you are going to think that these three are the same flower, right? Almost the same. Yes, exactly, right? So these flowers look the same, right? If you are if I like if I didn't mention these are three types of flowers, you still, like, you will think that okay, these are the same, right? So when you are going to define the features, right, the most important thing is that the features that you are going to define, right, the labels of the problem should be dependent on that features you are going to select, right? The color, no, they are not dependent on the color, right? So no matter what the feature you are going to do, select, that should be based, or there's those features, or I mean the labels of the problem should be dependent on that features, right? Understood? So therefore, this is what Ronald Fisher thought. This is what Ronald Fisher thought. So he saw this difference, right? He saw if you take the sepal and the petal, the sepal length and the petal length, sorry, sepal width and the sepal width, length and sepal width, petal length and the petal width. So if we compare these between these three types, he identify a major difference, right? So he selected features to be sepal length, sepal width, petal length, and petal width, right? Okay, so the features are also defined now. Here it's already defined, but if you have your own problem, you need to first identify the features and labels. So labels are straightforward. When you are going to identify the labels, that would be quite straightforward, but when it comes to defining features, you have to think a bit, right? You have to think a bit, and you have like select set of features and in such a manner that the labels should be dependent on that features. Right? You are going to select such a set of features. On that set of features, the label should be dependent on, right? So this data set is already available. What was collected several years back, almost 100 years back, right? So yeah, you can like see the see more details from here. But anyway, let me show you the data set. Right, so this is the data set. Right? Right. So if you like simply have an overview of this data set, there will be 50 setosa, right? 50 setosa flowers. and another 50 of versicolor, right? Another 50 of virginica, all right? So 50 versicolor, 50 virginica. Sorry, give me a second. Right. So there are altogether 150, right? Altogether 150, and each flower, you can see that they have recorded the sepal length, sepal width, petal length, and petal width in centimeters, I think. Got it? So they have measured it in centimeters, and also you have the label, right? So this data set is available. So what we are going to do now, all right? So we are going to now apply the things that we have already learned into this problem and train a K-nearest neighbor algorithm. But the thing is, I'm not going to explain how K-nearest neighbor works here, right? I'm not going to explain how K-nearest neighbor works here. But first of all, I will train a machine learning algorithm. I will train a K-nearest neighbor algorithm. Then after doing that, I will explain how K-nearest neighbor works, right? First, we will train a K-nearest neighbor based on this data set. And after training it and after completing the code only, I'm going to explain how K-nearest neighbor works, right? Okay. So shall we go to the now? The important thing that in this location, you should have this one. I mean, so do you have this iris CSV now? Don't worry about the other files. Do you have this iris CSV in your working location? This iris CSV in your working location? Is it there? Yes, 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 quickly. Is it there in your working location? Yes or no? Yes. This file is there or not? Yes. Is it there or not? The CSV file in your folder, the working folder. Ah, I'm very sorry. I haven't provided it there. Yeah, I just uploaded it, right? I just uploaded it. This iris.csv. I just uploaded it. Sorry about it. It was not there, right? Anyway, now it is there, right? This file, iris.csv. So I just uploaded it to a folder, right? I uploaded to here, the Google Drive. I think you have access to the Google Drive, right? To the day 4 folder I uploaded. Day 4 folder, right? Sorry, so can you get it from there? You can, right? Let me share it with you from the chat as well. I shared it with you from the chat as well. Sorry, I shared it with only one of you. Okay, right? So it should be included with your folders, I mean your files, right? So machine learning introduction file and this iris CSV should be there, right? Okay, so now the iris.csv. Okay, so now I'm going to go into a new file. No, not necessary, right? Not necessary. So but anyway, but I will build it so you can have a look, and later you can build it yourself, or else with me also you can build it. It's fine. But yeah. So I'll first use the pandas module, right? So for the purpose of loading the image, sorry, not the image, the data set, right? So first I'm going to load the data set into my code, right? So it can be done easily using the pandas module, pd.readcsv. So there's a function called readcsv, and what you have to provide is you have to provide the path of the CSV, right? The path of the CSV file. Then I'm going to get it here, data set, right? And so what I have done here, pd.readcsv. So what happens from pd.readcsv? Pandas module, readcsv function. So it loads the iris flower, the CSV file. I mean this, right? So the CSV file will be loaded. Make sure that it's in your working directory, right? So this is my code, and in the same location you have the iris CSV, right? You have to provide the the code, and the file should be in the same path. Otherwise, you have to give the path, the absolute path here, like what we did in image loading. Hope you can remember, right? Okay, so then next thing, this pandas as PD, the read CSV function available in pandas, load this data set into a something called a pandas data frame, right? Yeah. Any questions? Right. Is there any question? Okay. So this pd.read CSV reads the data set into something called pandas data frame, a data frame. So that's something special to the pandas library, a pandas data frame. But that's when you do it like this. But what you can do, you can do, you can provide something like dot values. So what this does, this loads the data set as a numpy array, right? So numpy arrays, we are quite familiar with numpy arrays, right? So let's see if dot values, this term, if dot values is not there, it loads into something called pandas data frame. You can do it using the pandas data frame as well, but since we are familiar with numpy, what we can do is we can provide the dot values, then it loads into a data set like this. So let's see. Right, so you can see it's loaded into a numpy array, right? Okay, so now can someone quickly uh, tell me, okay, what's the shape of this data set? The shape of this data set. Yes, any idea quickly? Yes. Yes, exactly. 155, right? So you know that there are 150 entries I explained you last time, and we have 5 columns. Why? 5 columns for like 4 features and a label. 4 feature and the label, right? So here, 4 feature and the label. Now here there's an important thing. Okay, that 0 represents setosa and 1 represents Virginica, 2 represents versicolor, right? So it's like a categorical, I mean, value is given, right? So we don't use, we won't, actually we are not using strings as label. So we have to always convert it to a number like this, 0, 1, 2, right? But it represents, like 0 represents for 0 represents setosa, 1 represents virginica, and 2 represents versicolor likewise.
So, sir, this is a problem with 3 classes, right?
Yes, exactly. This is 3 classes: setosa, virginica, versicolor.
Thanks.
Right?
Yeah.
Okay. Yeah. So these are the labels: versicolor, setosa, virginica, and these are the features: petal length, sepal width, petal length, and petal width. Right? So that's what actually given in this data set as well. Right. So right. And now we need to get the features and the labels separately. Now there's an important thing that I want to mention here is that now you know the features of this problem, right? You know the features of this problem: sepal length, sepal width, petal length, and petal width. And also you know the labels of this problem: setosa, virginica, versicolor, right? So these are the features, these are the labels, right? So what this means, right? But the values of the features, right? the values of the features, the numbers available in the features, this array, this 2D array, right? 2D array in the sense what? 150 into 4, 150 into 4. So this 2D array, like 150 into 4 in this case, right? 150 into 4 in this case, and this is known as data. This is known as the data. So this is a general convention, right? A general convention. And the values that you are going to find in the labels column, right? So this is a 150, a 1D array with 150, and this is known as the target, right? So the values of the features, right, is known as are known as data, and the target, the values, the numbers available in the labels are known as the target. Right? Got it? Got the idea? Right? So thing is now, these value now features are sepal length, sepal width, petal length, and petal width. Labels are setosa, virginia, versicolor. But the data set, in the data set, these numbers, these arrays are called data and target. So data simply represents the values available in the features, and the target represents the values of the labels. Understood? Right? Got it? Got the idea? Okay. So now the next thing, we want to get it separated. So we use indexing and slicing, right? Okay. So I want to get first 4 columns. Yes. Can someone suggest me how to get it? Yes, rows, all rows. Columns.
Can you hear me? Can you hear me?
Yes.
Actually, the fifth column, which is the
0 to
0 to 1, 0, 1 and 2, it is also a part of the 2D array, no?
Actually I can't hear what you say. Okay. Yeah, so 0 to, yes, 0 to.
Can you hear me now?
Yeah, I can now.
In the fifth column, which is the value label, it is also a part of the.
No,
You
no,
mentioned only 4 columns. There is also fifth column, no, which is a variable.
yeah. So these are the features. So 0 to 5, right?
Yes, yes.
So the upper limit is always 1 less than, you know that, right? So
yes,
then,
yes.
yeah. So then how to get the last column? All rows and
Fifth column. Oh.
exactly, very good, right? Very good. Now, if you print the data, 0, 0, 1, 2, 3, 4. Sorry, 0 to 4, right? So there are 5, but 0, 1, 2, 3, 4. See, now we have extracted only this. Right? 0 to 4. Now, see, this is where you are going to use it, right? So the things that we learned in our first few days, see, very useful, right? So these are the targets. Targets are simply the last column. The last column. Got it? Right. Right. Okay. So now any idea? Okay, now we have the features and labels. Our data set is now there, right? So now what we can do then? What's the next step? Any idea from your side quickly? Any suggestions from your side? Train. Yeah, train. But before training, we have to do one important thing, right? So we have the data set. Now I told you that we train the algorithm, but there's one important thing. Now, if you train this and if you apply it to a real world application, right? When you are going to apply it to a real world application, right? The thing here is that when you are going to apply it to a real world application, the issue is that we have to evaluate it first. I mean, training a machine learning algorithm from an existing data set, right? It doesn't mean that it's going to work perfectly, right? It's not going to work perfectly. For now, if you're going to do questions and you are going to get your, I mean, you are going to gain knowledge, but you are not going to go straight to the exam, right? You don't do that. So you have to like evaluate yourself before going on to the real scenario. Real scenario in like, if you want to go to a real exam, before the exam, you will be faced for some mock exams, some quizzes, or some term tests, right? So you have to evaluate yourself before going on to real world applications. Now, before concluding, okay, this algorithm that we have trained is giving good results. No, you can't conclude it. What you have to do it, you have to evaluate your algorithm, right? You have to evaluate your algorithm. That's the most important thing, right? You have to evaluate your algorithm, right? In order to evaluate the algorithm, right? In order to evaluate the algorithm, what you're going to do is you use the same data set, right? You use the same data set. What do you mean by the same data set? Using the same data set. What do you mean by that? That, okay, like this. Now, let's say you have an exam, as I mentioned in the first case, you have exam coming up in 6 years, sorry, 6 months, right? 6 months. And your teacher, right? Okay, in your school, let's say, right? So teacher takes 100 questions. Teacher takes 100 questions, right? So this is before going on to the exam. In order to evaluate in every one of your class, what teacher does, teacher gets 100 questions, and with the 100 questions, she has 100 answers as well. 100 questions, 100 answers, right? And the teacher selects 80 random questions, 80 questions randomly from out of those 100. 80 questions randomly, and corresponding answers also, like 80 answers also selected, right? So teacher selects simply 80 questions and 80 answers randomly from the 100 questions, right? And those questions and answers will be discussed in the class. That means you are going to train from 80 questions and 80 answers. Those will be discussed in the class, right? Those will be discussed in the class, right? Okay, done. So the training is done. Then the remaining 20 questions, you have the remaining 20 questions. After filtering the randomly selected 80 questions and answers, you have 20 questions and 20 answers. You have 20 questions and 20 answers. So those 20 questions will be given to you, right? But the answers won't be given. So the 20 questions, you have to write answers yourself. Still, I have the actual answers. The teacher has the actual answers, but teacher gives the 20 questions to the students and ask them to answer these questions, right? So the students, they are going to provide predicted answers, isn't it? They don't know the actual answers. They haven't seen this questions earlier. So they don't know the answers. So they provide predicted answers. Then what we can do, we can get those predicted answers and teacher compares it with the actual answers. Right? Teacher compares it with the actual answers. Got it? Then what happens? You are going to get a score. That's what happens, right? Usually that's what happens. Similar thing should be done. Why? Now, when you are going to get answers, when you are going to get scores, then after that test, you are going to get your scores, right? Then you can evaluate yourself. This is the level that I'm in. I'm having 95, score of 95. So I'm quite good to go to the exam. I'm having 75. I have to improve a bit. I'm having 25. I have to like do something else, right? I have to like change the algorithm. This algorithm is not working. Data set is not enough. I have to get more data and practice. Understood? Right? Got it? So if you are getting like 25, the algorithm is not working. The algorithm is not working for you. The algorithm is not suiting for you. But if you are getting 75 answers, if I improve some, if I do some questions, some more questions, I can improve this likewise. So based on the score, you have to say like, but if it is 95, you are fit to go to the real exam. That means you are fit to go to the real world predictions. For example, if you take a self-driving car, you can't first after training, you can't directly apply it to the real world. No, you can't do that. What you have to do it, you have to train the self-driving car, and before applying it to a real world scenario, you have to test it. Right? So what you do, you provide some answer known or the label known features and get the predicted labels, and the predicted labels will be compared with the actual labels and give you a score, right? So same thing should be done when you are doing machine learning. You have to evaluate the algorithm, you have to evaluate the training. Training a machine learning algorithm does not mean that it gives perfect prediction. No, you have to evaluate it, right? So therefore, we need to split the data set into two, training and testing. Like we did like 80% training and 20% testing, right? So there is a very useful function in Scikit Learn library, sklearn. The model selection sublibrary, we have a function called train test split, right? So what this train test split function does, when you provide data and target, and you have to provide another parameter called the test size, right? So what this means, test size, so these are like questions and answers, right? So it's like 20% of the question randomly selected, 20% of the questions will be kept, and 80% of the random selected data and target will be used for training, right? Test size 0.2 means 20% data and target will be selected randomly and they will be kept for testing, and the remaining 80% will be taken for training, right? So this train test split function return 4 things. First, data will be data. First, now this function, train test split function, return 4 things. You know, Python functions can return multiple things, right? Multiple returns. So this function return 4 things. This is how it's done. Data will be split into train data and test data. Like questions, 80% for training, 80% for testing. And the target now, right? Train data and test data. Got it? Train data and test data. Understood. So the data is now split into 2. Train data, test data, and target, train target, test target. So it returns multiple values. Same. Sorry.
Why are you repeating it twice?
Sorry. It will be target. Sorry, target. It should be target. So now this is how it happens. Data 80% for training, the remaining 20%, sorry, data 80% for training, the remaining 20% for testing. Target 80% for training and the remaining, sorry, the remaining 20% for testing. Same as the question, right? 80 questions for training and their corresponding answers for training, and 20% questions and their corresponding answers for testing, right? Now, let me ask you a question. The data, you know, it's 140, right? Sorry, 115 to 4, right? You know the data is, let's say, okay. Train data dot shape. Sorry, not train data, but data dot shape. 115 to 4, you know, right? 150 flowers and 4 features. So can you tell me, okay, what will be the shape of the train data?
So that would be 30,4.
What?
30,4 because we are taking 0.2 test size.
Yeah, test size. So train data will be like 80, right?
80, yeah.
Yeah, so that means 120, right?
That would be 120,4, yes.
Yeah, exactly. Very good, right? So train target?
That would be 80. Sorry, 120. That would be 120.
Yeah, exactly. Very good, right? So this is 150, 134. This is 24. This is 120 and this is 20. Sorry, 130 and 20, right? So train data dot shape, train target dot shape, test data dot shape, test target dot shape. You mean which line? This one? This one? Or this one? Second line. This one, right? So what happens now? We have given a test size of 0.2. That means 20%, right? 20%. 0.2 means 20%. So what happens? This data will be splitted, like for test data, 20% from the whole data set. And for train data, there will be like 80% from the whole data set, right? For train target, there will be 80% from the whole data set, and test target, there will be 20% from the whole data set, right? So since the data shape is 150, so there will be like 80% of the 150 columns, 150 rows, right? So that means 120, 80%. And 20% from 150 is 30. Got it? Okay. So now we can get the machine learning algorithm from sklearn dot neighbors import k neighbors classifier, right? Then so this is loading the k neighbors class, right? So this is creating k. I will explain what k nearest neighbor means, but this is a machine learning algorithm, a supervised type machine learning algorithm. So creating a creating a k-nearest neighbor algorithm object. So this is our k-nearest neighbor algorithm. Now, then, so we have the algorithm loaded now here, right? We have the algorithm loaded. So this is the machine learning algorithm. So this is that blue color box. This is that blue color box. So any idea now how to train this? Then the next thing is to train, right? So we have the algorithm. So now we are going to train it. So here you can give any customized name, right? But I use model, right? I use model, but you can use any customized name. It's fine, right? Okay, now then, can you tell me, okay, model.fit. Model.fit is the function that you are, sorry, method that you are going to use to train an algorithm. So what you need to provide here?
When you are going to train, algorithm, what you need to provide?
So that would be data train and target train.
Very good, very good. Train data and
Train target. So features and labels, right? Features and labels. Okay. Done. 1 second. Less than 1 second, the training is done. I will explain what happens inside. I will explain the theory behind the k-nearest neighbor. But for now, I will simply explain the code. But later, I will explain what happens inside this training and what happens when you are going to train it and how the prediction is done. So I will explain them. But for now, just I'm explaining the code, right? Step by step. So then you have to evaluate it, right? Evaluate it. But if in order to evaluate it, right? See, now how to get a prediction from a machine learning algorithm? So can you remember when you train, you pass features and labels. When you are going to test, you are going to only pass features, right? So now, what are the, I mean, can you remember the set of labels that we have? The features that we kept some set of features, right, in order to evaluate our model.
That would be the test targets and
Test data, the questions.
test data. Yeah, test data.
We provide the test data, and what machine learning algorithm provides us? So when we provide like test questions, what the machine learning algorithm provides us?
Test answer. Target answer.
Yeah, it provides us some predicted answers, right?
Predicted answers. Yes, yes.
Predicted answers, some predicted answers now. So teacher has 80 questions out of 100 questions, 80 randomly selected 80 and questions and answers. We trained our brain, we trained our knowledge. Thereafter, teacher provides us some test questions, 20 test questions, and we provide predicted answers, right? Done. So now we are going to evaluate ourselves. Now, where the teacher, I mean, the teacher has the real answers for this test data. Where is it? The real answers, the real labels for this data? Yeah. So the actual labels are there in the, oh, now here can you see? Okay. For training, train data and train target. For testing, we has, I mean, for test training, we have train data and train target. And we test the model using the test data, and we have the actual answers for those test data, actual labels for those test data in the test target, right? Okay.
Yeah.
So this will be the actual label. And the predicted labels? sorry, predicted, let us like predicted target. So these are the actual and predicted. So the answers provided by the machine learning algorithm and the actual answers, right? Seems quite the same, right? Seems quite the same. But the thing is that we can't get a clear idea since we like 30 values are there, right? So this is not the method of evaluating, right? We have a metric. We have a metric. What's the metric? The accuracy metric, right? So what do you mean by the accuracy metric? We can measure a parameter called accuracy. So accuracy what? Number of correct predictions divided by number of total predictions. For example, we have number of 30 total predictions, and we are going to measure how many correct predictions are there. So this is what we call the accuracy. I'm not saying like 28 correct. I'm just assuming, right? Anyway, like the number of total predictions in this case 30. So we are going to check how many correct predictions are there in the, right? So this is what you are going to, I mean, this is how we are going to get your marks for exam, right? Isn't it? Right? So number of correct answers over total answers, right? Isn't it? Simply, right? So we have a inbuilt function, no need to do it manually. So we have inbuilt function in Scikit Learn from sklearn.metrics. So this metrics submodule contains the the performance metrics like accuracy, R2 score, classification report. So in order to evaluate our models, this sklearn.metrics has several functions: accuracy, R2 score, F1 score, precision, recall. Likewise, lots of evaluation parameters are there, performance metrics are there. I'm not going to talk about everything, but I will get the accuracy score. I mean, accuracy score is not the only method of evaluating a model. We have some other methods as well, but here we are only discussing about, right? So we have to provide the actual labels as well as the predicted labels. Sorry, predicted target. Then you can print the accuracy. Right? So what this means? 96%, almost 97% of your predictions are correct. So that means what? 30 into this, how much? Almost 29 is correct. Only one is wrong, right? So if you compare these values, right? Correct. Okay, now let me show you one thing, right? If I run the whole code again from the start, now you get accuracy of 1. What's the reason? Can anyone predict what's the reason?
Is it because it's segregating the data in a ordered fashion? Like it's taking the same set of data?
No.
It's not using a random generator.
Yeah, exactly. Very good, right? So the thing is now here you can see I told you that this train test split is done randomly, right? So that means going to get a different set of training and testing in the next case. So if you run it again, sometimes you will get a low accuracy.
Yeah.
Right. Now we are getting always 1. Yeah, 96. Sometimes. Right. So it changes, right? It changes since the train test split is done different, right? So 93 now. right? So likewise, that this is before, this is due to the random data splitting, right? Okay, so now 99, if your model gives, this is application dependent, but if your model gives more than 90% accuracy, that simply says, okay, this is a good model overall, right? But it's always
Can we
like,
use k-fold
yeah, you
validation
can,
method?
you can use k4 method and get accuracy.
That will divide them into further n pieces, right?
Yes, exactly. So that also can be done in order to get a better
Better.
but the accuracy is always accuracy R2 score, whatever this evaluation parameter is application dependent, right? So if your application is something kind of a self-driving car, what? You need to be precise, right? So you need like 99% you have to achieve.
Yes.
Right? But if it is like this kind of a thing, it's fine. I mean, right? So
yeah, I think when it comes to healthcare, I think it has to be more accurate.
Yeah, so it's application dependent always, right? But overall, we can say if it is greater than 90%, it's quite good, right? But it's like this now. Let's say you are going to develop a model to cancer detection or something like this, but your model gives 92% accuracy, but there is already existing method which gives 97, so your one is useless.
True.
So if there is already existing model, if you are going to build the same thing, you have to achieve more accuracy than that, right? So 90%, I'm just saying 90%, it's if it is higher than 90%, it's good. That's overall, like generally I can say, but it's always application dependent, and also like it's dependent on the already existing methods as well, right? Okay, so good. Now, yeah, so this is how simply you done. Now 93, I can say it's a good model then, right? So then this is how we are going to get a real world prediction. Model.predict. So you have to pass it as a 2D array, right? And you can provide a sepal length. I'm just assigning some random values, right? Sepal length. You are going to get a flower and some, okay. This is how now, okay, now we have done the evaluation. Now you can go to the real world predictions. Now you can get a flower and you can get the predictions, right? So it says what? What do you mean by 1? Huh? It says this is a Virginica, right? Got it? So result is 1. So it says it's a Virginica, right? So this is how you are going to get future predictions. Right? This is how we are going to get future predictions. But before going on to future predictions, before using it as a real world model, the most important thing that you have to do is that you have to evaluate model it and verify your model is giving results, right? So then you can get future predictions. Understood, right? Okay, good. So any questions, any unclear point, or anything I need to explain again? So this is how we are going to simply train a machine learning algorithm. Now still you don't know how Knearest neighbor works, but I will explain. I'll explain. Okay, so then let me quickly explain what Knearest neighbor algorithm and how Knearest neighbor algorithm works, right? So still, though we have trained algorithm and though we have evaluated the algorithm, we still don't know how the Knearest neighbor algorithm works, right? So now what we are going to do, we will quickly move on to the Knearest neighbor algorithm, the working principle of the Knearest neighbor algorithm, right? So can you all give me a second? Okay, right. Yeah, right. So K-nearest neighbor algorithm, we will discuss everything from the beginning about the K-nearest neighbor algorithm. So K-nearest neighbor algorithm, or the KNN algorithm, we say, is one of the simplest, easy to understand machine learning algorithm. But said that it doesn't mean that it's a less accurate algorithm. No, it's a very accurate and a very, well performing algorithm. The only thing is that the working principle of the K-nearest neighbor algorithm is quite simple. That's why we have selected it here, in order to give you like a good understanding about a very basic algorithm, right? As beginners, it quite suits you, right? So K-nearest neighbor is I will explain that later. So K-nearest neighbor used in most, like it's known good for finance applications, healthcare applications, political science applications, handwritten digit recognition, image recognition, video recognition. So those kind of applications, KNN algorithm said to be good, right? Like it's I'm saying like from past applications, past projects, so they say, so, okay, K-nearest neighbor is good for those kind of applications, right? So it's like mostly used in finance sector, right? For loan disbursement. What do you mean by loan disbursement? Now, when there is an application for a loan from a client, banks check whether this person is capable of settling this uh, loan, right? So they have lots of data, like the history past, the past data of past customers, past clients, like the amount of the loan they have applied, the age of the client, and the monthly income, and everything. Likewise, lots of data available, right? So they have also the label is also there, right? So they have successfully settled the loan or not, right? So likewise, if we have this kind of a data, so K-nearest neighbor can be used like when a new client comes. So the same data can be applied, okay, like the age, the monthly income, likewise, lots of several factors, and predict whether this client is going to repay or settle the loan or not. Likewise, for those kind of applications, K-nearest neighbor is used. So those are the well-known applications of K-nearest neighbor, right? So yeah, used for most applications. And now first what we are going to do, we will understand how K-nearest neighbor works. And I want to explain you, like now I told you that we have to change only 2 lines, right? We have to change only 2 lines in order to change the algorithm. Everything is the same. We have to change only 2 lines in order to change the algorithm. So I will explain it later how to do that, right? First, we will get to know about K-nearest neighbor algorithm, right? So let us get a sample data set. So in this sample data set, what we are doing, that we have the same problem, the temperature, humidity, the rain or no rain problem. But I have assumed that only 2 features are there. So I have simplified this problem. I have simplified the problem, and I'm assuming that only 2 features are there, the temperature and the humidity, right? The temperature and the humidity. So the temperature and the humidity, like let's assume those are 2 features, and let's say that we are going to provide this into the machine learning algorithm, right? Machine learning algorithm along with the labels, right? So let's say this kind of data set is given for training, right? So in the machine learning algorithm now, don't think that the machine learning algorithm is going to plot this kind of a graph. No, machine learning algorithm is not going to plot this kind of a graph. I want to explain you how this how this done. So that's why I have plotted the graph here, right? Give me a second. Right, I have plotted a graph here. So two axes like temperature and humidity, right? So two features. So the features are represented in the axis, right? So this is the feature 1 and feature 2, right? And then you can see the label is represented from the color, right? Rain data points are represented from red, and no rain data points are represented from uh, green, right? Green. So what happens here simply, so what happens here that the training data now, this is the plot of the training data, right? So training data will be placed something like this. Now, when we have a data to be predicted, I'm assuming only one, right? So I'm having a one data to be predicted. So let's say that today, the temperature and the humidity of today, right? So what we are going to do, now we'll get the trained data to be predicted, right? Right? So we'll get the features, right? So you know, simply here, this model, can you remember? Right? So we passed the features. Now here we have assumed that only two features are there, right? Got it? Right? So then what happens? We are going to place it in this graph. Let's say we are going to place it in this graph, right? Now what happens? Now I think you get the idea, right? What's the name of the algorithm? K nearest neighbor. Let's keep the K. We will discuss about K later. Nearest neighbor. So what happens? We have a data to be predicted, which is shown in the blue color, right? And it's like 33, 35. The temperature is 33 and the humidity is 35. So you plot it in this graph, and you are going to look for the nearest neighbor out of the trained data, all the trained data. So we are going to go through all the trained data and see who is my nearest neighbor. Who is the nearest neighbor to this data to be predicted? Right? Got it? So what is it? Who is the nearest neighbor? Is it a
Those first three green points.
Yeah, is it a red one or a green one?
No, those three green points.
I mean, I must nearest, the nearest.
Nearest.
You can see.
Okay, the one on top, the red.
Yeah, this one, right? So nearest. So what
That
happens?
one.
So okay, the nearest point to the data to be predicted is a green one. So that means it will be predicted as a no rain.
No.
Since there is the nearest, I mean the nearest one is a no rain. Right? Now, the idea here, okay, the machine learning algorithm is not going to like see this kind of a graph. We can see, we can see once a graph is plotted, we can see, but the machine learning algorithm, no, it has some data. It has some data, it has some points only, this kind of X and Y. This kind of X and Y are there, right? X and Y are there. So what's going to happen? The machine learning algorithm like can't get this kind of a feedback. Therefore, what's going to do? It's going to measure the distance to all the data points, all the training data points. It's going to measure the distance to all the data points and select the distance. Which distance?
The nearest.
That if you take like the distance, in terms of distance, the minimum, right? The minimum distance, right? So,
but how will it define the minimum?
You are going to, you are going to measure the distance from the data to be predicted to all the training data points, right?
Okay.
All the training data points, the distance will be measured to all the training data points from this blue color point, right?
Okay.
Then out of all those distances, the minimum distance will be selected, and the corresponding data points for that minimum distance will be the prediction. The label of that data point will be the prediction, right? So anyway, how this distance is calculated? Like this. How? What this distance measurement called?
Pythagoras theorem?
Yes, exactly, the Pythagoras, right? So -60 minus 35, I think, is square 28 minus 33. So this is called the Pythagoras, right? The Pythagoras distance. So Pythagoras distance will be measured for all the points and select the data point with the minimum distance. Select the data point with the minimum distance, and the label corresponds to that minimum distance will be given as a prediction. Understood? Right? Right? Understood, right? But the thing is now, okay, I think you are familiar with this, right? So it's going to select the minimum data point, measure the distance to all the data points and select the minimum distance, and the data point which has the minimum distance, the corresponding label will be taken and the label will be given as a prediction. For example, now it says no rain. Understood, right? But the thing here is when it comes to a practical problem, we can have more than 2 features, right? Isn't it? We can have more than 2 features. For the example that we took also, we had 4 features. The sepal length, the sepal width, the petal length, and the petal width, right? We have 4 features there. Therefore, how to deal with that kind of a problem when you have multiple features, right? When you have multiple features, how to deal with that kind of a problem? Let's say, for example, 4 features. So let's say that this is the data point 1. Let's say that this is the data point 1. And this is the data point 2, let's say. Right? The data point 1 and data point 2. Got it? So how the distance will be measured here? So similar to the Pythagoras, but here you can see the difference between the temperature square, difference between the humidity square, the difference between the wind speed square, the difference between the light intensity square. So you will be getting like this. See, 36. See. So like in Pythagoras, we have only 2 features, right? Two axes, but when it comes to this method is called the Euclidean distance, right? Euclidean distance. So what happens in the Euclidean distance? Number of features is not going to be a matter, right? what happens? It's going to measure the distance, right? It's going to measure the distance between each and every data point, right? It's going to measure the distance between each and every data point, right? Each and every data point, and what happens? I mean, each and every feature, the temperature difference square, humidity difference square, wind speed difference square, light intensity different square, and the square root. So this is known as Euclidean distance. So Euclidean distance, no matter how many features are there, you can take the distance, right? So this is what you call the Euclidean distance. And Euclidean distance, like when dimensions, like when there are two features, that becomes Pythagoras. But Euclidean is actually defined for like any number of features. You can go with any number of features, right? Got it? So this is how you are going to deal with multiple features when you have multiple features. But the thing here, right? The thing here is that you can't you can't
Hello.
you can't visualize these four features, right? I can't visualize four features and show you the distance. The maximum number of features you can visualize is 3D. Other than that, you can't visualize, right? So any questions you have? Seems you have, right? No.
Hello.
Yeah.
So if the low Euclid distance means those labels are preferred, is that it?
Sorry.
So if we given any inputs like 31 comma 33,
Okay.
so the nearest what we say features will be compared, and the which has the low Euclid distance, those label will be preferred.
Yeah.
Like,
Exactly. Now this is a sample. Now I wanted to show you like how to get the Euclidean distance between 2 points.
okay, fine.
But anyway, now when you have multiple features, what will happen? The distance will be measured, the Euclidean distance will be measured for all data points and select the minimum data point. I mean the the data point which has the minimum distance, right? I mean, the thing is, when you have two features, you take the Pythagoras, but when you have more than two features, you get the Euclidean distance. So you are going to get the difference between each feature and square it and add them together and get the square root. So that's what you call the Euclidean distance, right? So it can be done for any number of features, but Knearest neighbor algorithm is not used when you have large number of features, right? Like 1,000, 1,500, more, like large number of data set, large number of, I mean, the problems which has large number of features, we don't use the Knearest neighbor, right? And
So
yeah.
all these what we say distant Euclid distance formulas are like inbuilt in
Yeah, this one.
this
I mean,
algorithm.
yeah, the thing is now, no matter what the feature, it will automatically like assign it inside the code.
Okay, fine.
So then K, what do you mean by K, right? So assume we have this kind of, unfortunately, like it's a very rare case, but we have this kind of a situation. Now, according to the theory that I have discussed up to now, can you like identify what the prediction will be for the blue color point? Yes.
It would be rain.
It would be rain, right? So that means the nearest one is the red color one.
Yeah.
But is it fair to give that kind of a prediction?
No, I think we'll have to have more data.
No, it's not. Why? You can see the blue, I mean, the data to be predicted, the blue point is surrounded by green color points. That means no rain points. But unfortunately, you have one rain data point here, right? So these are called outliers. Yeah, outliers. What I mean by outliers, now, sometimes there can be like a very sunny day, but around like 10 p.m. there can be a rain, right?
Yes.
So those kind of days might be there, right? So similar like real time, I mean, very rare, but possible. But these kind of things can be happen. So in that case, this is not a fair prediction. So therefore, we can overcome this. We can avoid this kind of things, right? So how we are going to do that? We have a k that we never discussed up to now, right? So we can, like in the default case, k will be 1. What do you mean by k is 1? It's going to select the nearest one. It's going to select the nearest one nearest, right? One nearest neighbor. But you can provide k usually a odd number like 3, default 1. By default it's 1, but you can override it. You can provide 3, 5, 7, 11, likewise 9, 11. But like usually we provide a odd number, right? So what happens when, for example, when k is 3, it's not going to select the nearest neighbor, but it will select 3 nearest neighbors, right? It will select 3 nearest neighbors and get the majority, right? So here it's going to get the 3 most nearest neighbors, right? 3 most nearest neighbors, and the algorithm checks how many, like the majority. Now here, if you take the majority, 2 rain labels are there inside the 3 nearest neighbors. So now the priority is given to the, not the nearest one, but the majority. So according to the majority, there will be 2 no rain days inside the 3 nearest neighbors. So the prediction will be given as a green one. That means a no rain.
So is this k very subjective? The k value?
Yes,
we
exactly.
can,
It's actually application dependent. I mean, we can't
for
exactly.
example,
Yeah.
For example, let's say instead of those 3 points, if I have 3, since they are classes, right? So we have 2 classes, rain and no rain. Let's say if I have 3 classes and those 3 points are 3 different class, then what can happen?
Yeah, then you can usually provide the kind of a higher value. Okay, 5.
So can you
Okay, 7.
show us in the algorithm where we can feed in this k value?
Yes, exactly. Now,
Because
yeah,
we can't see that graph, right?
yeah, this is where you can provide the k value. The parameter is n neighbors.
Okay.
Right. Now, for this example, I don't think that this makes a much difference.
Yeah.
But for other applications, so there's a method of, selecting the best k value. That's called the elbow method, but not a very successful method. But what you can do is, like, if you are getting a low accuracy and if you are like feeling that this is not working well, you can change this k value and see whether you can get a good result, right? So most of the times we have lots of parameters to be adjusted in machine learning algorithms. So the only method is trial and error. Trial and error in the sense we have to change those parameters and see. Since we can't have like optimal values, since the algorithms, their behavior depend on the application. So if the k value is good for the rain no rain problem, it can be like not good for the iris flower example. Likewise, it's application dependent. So we can't say this k value is the optimum. No, it's application dependent, right? Got it? So anyway, this is what we mean by k. Right? So simply then k, how you are going to calculate distance and find closest neighbors according to the k value, and out of the nearest one, you are going to get the majority, and according to the majority, you are going to get the prediction. By default, if you don't pass anything here, that will be considered as k equals 1. Understood? Right? Got it? Okay, so quickly, any questions?
Hello.
Yes. Sorry.
Can we implement this algorithm with any iris photo?
Sorry.
Can we test this algorithm with any photo of iris?
Yeah, you can do that. You can do that. I mean, without getting numerical features, you can get directly a image, right? You can get directly an image. So um, then the features will be taken as the pixels, right? Each
Okay.
pixel of the image.
Okay.
So we are going to like do a similar example so you will understand actually, right?
Okay.
I think this is available in your right. So the thing that we are going to cover yeah. So this is what we are going to do now, right? So we are going to go on with advanced application, handwritten digit recognition, right? So in this one, right? So you know about images. No need to discuss anything about images. I think you are familiar with images, how the images behave, right? So this is the problem that we are going to get: the handwritten digit recognition, right? Handwritten digit recognition. So how to perform handwritten digit recognition? Uh, how to train the algorithm for handwritten digit recognition, right? So here now the problem is handwritten digit recognition. So you know how first the thing, I mean, when you have a problem, you have to first analyze it's a classification problem or regression problem. So I think that you already know that this is a uh, classification problem. We discussed about this as well, right? So this has 10 labels, right? So any handwritten digit, single digit,
Hello?
can be like anything from 0 to 9. So that means 10 possibilities are there. So then 10
Hello?
labels are there. Yes.
Hello?
Yeah.
One small note regarding previous
Yeah.
that iris.
Yeah.
So if we implemented that algorithm using Knearest number, so then how to complete that implementation of detecting the, I mean, we for just testing we gave our own input like something random input, but to implement the truly implement that algorithm, how to proceed?
Yeah. So
I
I
mean,
think,
for testing that
yeah.
we
So
give
I
all
think,
those inputs for of our own, but while coming to reality, how to use that algorithm?
yeah. So very good question, right? So very good question. Now, how to like implement this for a real world application, right? So thing is now,
Yes.
I probably discuss it about about that here in this example, right? So here finally now after training this algorithm, you will see that
Okay.
at the end we save it to a physical file. The the trained algorithm, right? The trained algorithm,
Yes.
we are going to save it to a physical file, and
Okay.
the primary objective is to create a web application like I mean, for example, uh, something that I some like something that I showed you, right? So here,
Yes. Sir.
right? So this is
Okay.
a real world application, right?
Yes. Yes.
So for this
So
kind of,
while we give input this from this web app, those inputs will be sent to the algorithm and tested. Is
yes,
that it?
exactly. So that's like model deployment. So anyway, I think I probably discuss it here, right? So then you will understand how to do it.
Yeah, sure.
Okay.
So
Yeah, so that's actually what we need to do, right? So rather than training it in Python code and getting results like some random inputs, so what we have to do is we have to implement in a real application. So that should be the target, the ultimate goal. So I will anyway explain it from here, right? Okay, so data and target. Now first we will analyze this problem. So all the answers, the answers for all the questions, you will get it from here, right? So the idea here that we are going to train this data set, the data, get a data set and define the features and the target. So the target straightforward. So we have like, in order to detect handwritten digits, there will be 10 targets, 10 labels, 0, 1, 2, 3, and 9. So 10 targets will be there. So we have a question here. What about the features then, right? The features. Usually when it comes to images, right? Images, the raw pixel values will be taken as features most of the cases. Not, some of, yeah, I can't exactly say, but most of the cases, I can't give you like a percentage, but most of the cases, the images will be taken. If something related to images like face detection, face recognition, object detection, character recognition, so the image based things, when it comes to image based things, the raw pixel values of the images will be taken as the features. Not all the cases, but most of the cases, right? Some cases like involve feature engineering, we apply feature engineering techniques like to, in order to get the features extracted, like the edges, lines, corners, likewise, right? But most of the times we apply the raw pixel values, right? So we apply the raw pixel values. So here what we are going to do is we use a 8 by 8 image. So 8 by 8 image. So the features for a single data point will be an image. So for this example, we are going to use 8 by 8 image. One 8 by 8 image for a digit, right? So how many pixels will be there then? Very straightforward question. How many features will be there?
So can you please repeat the question?
Yeah. So now my question was, okay, we have defined the labels. Okay, labels will be 0 to 10, 0 to 9, right? But features, how to define the features? Usually when it comes to image-based applications, right, we take the raw pixels as features, raw pixels, right, as features. So in this case, we have a data set with 8 by 8 images. The resolution is 8 by 8 images. So how many features will be there in our problem?
That is 64 pixels.
Exactly, 64. Now, don't get the idea wrong. Don't think for all the application, okay, then face detection, face recognition. So you are going to get face images and define the features as the pixels. No, not all the applications, but most of the applications we use the raw pixels as features, right? But sometimes we have like do some feature engineering and feature extraction methods should be applied. But here is not the time to talk about them, right? So we will probably in a coming workshop uh, about full machine learning workshop, we will probably discuss about those things. But here we will only discuss about this level. So, but keep the idea, when it comes to images, we will use the raw pixels as features, but not in all the cases. Sometimes we have to apply some feature extractions things, right? Okay, so anyway, here then you can take the features, if you take a single image, it will be like all the pixels of that image. So therefore all the images should be in the same shape, right? Same shape, like 8 by 8, all the images should be 8 by 8. Otherwise, now you know that 64 features will be there, but if the size changes, the number of features will be changed, right? So all the data, every data point, I mean every digit, you have to have 64 features. So everything should be in the same size. Okay, so how to find the data set? We have an inbuilt data set for this, right? So we don't use a external data set. We have an inbuilt data set for this application provided by Scikit Learn. Now, this is not for all the applicants. So if you want to develop your, like, let's say you are going to detect Hindi characters or Tamil characters, the letters. So it's not, inbuilt data set is not available. So this is for digits. So digits, there's an inbuilt data set available in Scikit Learn. So what we'll do is, from the sklearn.dataset, import load digit. So this is a function we can use to load the digits dataset. So this dataset is coming as an inbuilt dataset for Scikit Learn. So it's provided like as a toy dataset. We can apply this dataset and train our application. So it comes as an inbuilt application, inbuilt dataset. So this function load digits, what it simply does, it loads this data set, it loads the data set here, right? And we have inbuilt methods. Now, this scenario will be like different when you are going to deal with your own applications. You have to manually get the images, and the images are in different data, different resolutions. Some of them are 50 by 50, some of them are 100 by 50. We have to apply pre-processing, we have to read all the data, we have to crop the data, we have to do lots of things when it comes to our own data set. But here, right, we are quite, our life is quite easy here. We have a inbuilt data set. So inbuilt data set, we have to just load it, right? So in this data set, we have three things: the data, images, and target. So data and target quite straightforward to you, but images, what do you mean by images? I'll explain. So again, since this is a inbuilt data set, these are already available. So one shot, you can call like dataset.data, it gives you the data. Dataset.images gives you the images. Dataset.target gives you the targets, likewise. It's given by the library, no need to worry, right? So you can see when you run this 1097 8 by 8, 1797. What this means now, I will explain images, right? So this means there are 1797 8 by 8 images. 8 by 8 images. So this means that, can you remember 154? What it means? 154. 150 flowers. Each flower has 4 features, right? So here also what? Okay, 1797 images. Each image has 64. Right? Got the idea? So this is the 2D version of the image. This is the flattened version of the image. Let me show you, right? Let me show you. Right? What is this? Right? So I'm going to show you the 100th image. So we have 1797. From that, I'm going to show you the 100th image. So this is the 100th image, right? So if you print this is what you have. Like, can you see 8 by 8 numbers, right? 8 by 8 numbers. So when you show it, you are going to see this kind of a digit. But actually, this is what you have. Now, if you print the data, what this has, it has a flattened version of this 8 by 8. What I mean by the flattened version? So 64, 8 by 8, you have the 8 by 8 image. So the data contains the flattened version of each image, right? So this images contains the 2D version. This data contains the flattened version. What do you mean? This is how the flattening is done. Flattening is done. See? This is how the flattening is done. This one here. This one here. This one here, right? So you know the flattening, right? 8 by 8 into a column vector. Sorry, a row vector. This is how the flattening is done, right? So data contains the flattened version, the 64, right? So this same thing flattened, right? So can you see it? 64. This is the requirement now. Deep learning or neural networks can get 2D images. But unfortunately, most of the machine learning algorithms can't get a 2D version, so you have to flatten it. So if it is a 50 by 50 image, you have to convert it to 2500. If it is a 100 by 100 image, we have to convert it to a 10,000, right? Got it. So here, now we don't need the images, but in order like just show you the images, that's why this 8 by 8 version is available, right? But anyway, what we use is this 64. So this simply says, okay, iris flower example 150. Each flower had sepal length, sepal width, petal length, petal width. So here 1797 images. Each one of them have like 64 features, the flattened version. Yes. In deep learning, you have to build on your algorithms. That means you have to design the neural network. All the tools are available, but neural network you have to design yourself. Right? So now this is the data 100 and this is the target 100. So what the target means? What the target means?
Is the answer. I mean, the output.
The digit, right? The label.
The digit.
So it's a 4, it says, right? So now if you like provide like, okay, the 1796, the last image. Let's see what the last image is about. I can't exactly understand, but I identify, but I think 8 is it? No, it's also a 4. I don't know. It's 8. Right? Got it? So nothing to worry. Similar to feature, I mean, similar to the mesh, I mean, the iris love example, but more features, right? The features here, pixels, directly pixels, the pixel values, the raw pixel values, right? So what we'll do, we train test split, the usual thing we know, right? Train test split, and what we do then? K-nearest neighbor algorithm. We take the K-nearest neighbor algorithm and we train it for n neighbors, 3n neighbors, and test data we apply to the algorithm and get the predicted answers. We test it and we measure the accuracy. Very good, 99% accuracy, right? So that means what?
Sir, on what basis did you give n neighbors is equal to 3?
Yeah, just I wanted to show you like n can be used here.
Okay.
So out of 360, why 360? What? 20% from 1796 is around 360, right? So 99 of them are correct. That means 356 answers are correct. That means almost like 356 answers are correct. Digits are out of the 360 prediction, almost 356 digits are predicted correct, right? Now the most important thing, now we have trained the algorithm. Now the training part we have done already. We have done this earlier. Right? Got it? We have done this earlier. The data, the train test split, can you remember? We have done this earlier in the array flow example. Now, if you can get the data and target, the code the same, right? You have like define your data and target. That's what you have to do. After defining the data and target, the normal code that you have to apply, right? So here, now what I want to show you, if you use support vector machine for this, you have to change only 2 lines. See? So you can apply different algorithms and see how it works, right? See, only 2 lines changes. Right? So the last part, this one, quite important. Right? The answer for the question that you asked. Okay, so we have trained the algorithm. So what next? How we can use it for a practical application? In order to use a practical application, now the code that we have done up to now is a development, kind of a like testing, machine learning algorithm training, right? So after training, the most important thing is that not the knowledge. I mean, sorry, not the data set. For example, right? For example, now if you take like, let's say that, okay, you are going to read 100 books and you are going to get the knowledge from that 100 books, right? So now after that, do we need that books? If you got the knowledge, where your knowledge will be saved? It will be saved in your brain, right? Similar here. No matter how large your data set is, the database is not going to be a matter after training your algorithm. The knowledge is in the model. The knowledge is in the model, right? So what do you do? Huh? So what do you do?
We need to save the model.
We
so
save
that
the
we can
model
use it for future
into a
purpose.
physical file.
Okay.
This is the most important thing. After training a machine learning algorithm, get this file. So everything is done after now. We have a trained model which can give you like almost 99% accuracy. So this is like something you got from almost 200 images, the knowledge you got. This is what important. Not the books, the brain, I mean your knowledge, your memory is important, right? So now what do you do? We can use this model in a web application. We can use this model in a mobile application. We can use this model in anywhere you want and use it in a real world application like this. Let me show you. Um, um, sorry. Now, don't worry about this. I will explain this in your take-home tutorial. Sorry. What I'm doing here, I'm running the now we have developed a web application here. A website, right? A web application. I'm not sure this is giving you the correct prediction. No. The thing is, I think there is some issue with the, I don't know, it's giving predictions, right? Sometimes it's not giving you correct predictions, but most of the times it's giving correct predictions, right? So this is a good application, right? So that file, the model file that we saved will be used in this web application, right? So I will explain how to do this in your work, take home assignment. Now I will talk about this a bit. So joblib is the module that we are going to save machine learning models into physical file, as well as load machine learning models into a code. We save here, but in the web application we load this model. For saving and loading, we use the joblib module, right? So what we have to do, joblib.dump. So joblib.dump is the function that we use to save a machine learning algorithm into a physical file. So this is the algorithm name, the model name that you use, right? So you save it. This is the file name, the physical file name, right? So if you are wondering, okay, what this file type is, you can't actually view it, right? So if you try to view it using some kind of it's some kind of encoded version, right? So this is a machine learning model. You can't view it, but it's an encoded version, but you can load it into your own application, right? You can't view it. You can't view what that file type is, but it can be loaded into a loaded back, right? Okay, so that would be it, right? So today, take home assignment, we will discuss about how to create this kind of a website, right? And how to create this kind of website using Python, and how to load the trained model here. So that's a real world usage, a real world application. What the algorithm that we train using some data set, how to use it in our real world application, right? Okay, so that's it. So now it's time for any questions if you have any. Right? So I'll share my email address with you, right? So you can ask if you have any doubts, any concerns, any questions. If you have, you can always contact me, right? And keep in touch. We will be like, now this is like the introduction for machine learning, right? Yeah, the Flask topic, this Flask topic will be like, this is what the take home tutorial is about, right? The take home tutorial is about the Flask. That will be like 1 hour or 45 minutes tutorial, right? So how to develop a back end using Flask, right? That will be your take home tutorial, right? So the next thing is that what I wanted to highlight here. Yeah, so now this is kind of introduction to machine learning, right? So if you are interested in these fields like deep learning, neural networks, machine learning, we have some future workshops coming, right? So you can participate them and get in-deep knowledge, right? The in-deep knowledge, but here we are only discussing about the introduction, right? So if you want like explore more the in detail learning, then you have to like it's better if you can participate in the workshop. So we will keep you updated about that, right? And the thing is, now here I'm going to conclude the live session, but you will get the tutorial how to implement a Flask module and using how to create a backend using Flask and how to implement this kind of a website, right? So we will discuss about that in the take home assignment. And the other thing is, I wish you all the best for your future, right? So thing is, now we have covered lots of things out of this, in these five days, right? We have covered lots of things like the basic Python, the Python modules, image processing, machine learning, and also today you will get the web development tutorial as well, right? So the thing that I want to highlight here, right, that this is a very useful field that we are going to, that going to come in the future, right? A very useful topic, machine learning, image processing, data science, neural networks, right? So the thing is, now the things that we have covered, you have to find a method to apply these into your applications, That's the most important thing. Or just following the code that I have covered, or just doing the examples that I have done, that won't do anything. You have to think a method, or you have, like, if you have your own ideas, you have to use the things that we have learned in this workshop, and you have to use those things in real world applications for your own applications. That's how we are going to learn new things. Otherwise, just following these things won't help you, right? Correct. So the important thing is to, like, somehow try to apply this for your own application, the things you have learned, right? Okay, so we have a question. Yeah, so my LinkedIn profile, and yeah, I think I have it here. Yeah. Give me a second. Right. So any other questions from your side?
No, sir.
Yeah. Yes. Yeah. So I'm teaching all the machine learning, and yeah, so I'm doing the machine learning and deep learning workshops. All the contents I will be covering them. Same thing.
So when is machine learning or deep learning workshop? Do you
Sorry.
have any? Do you have any upcoming deep learning, machine learning
Yes,
workshop?
exactly. We have. So we will inform you. We will inform you. Like, not the dates are not fixed yet, but we will
Okay.
share emails with you, and we will inform you.
Okay. Thank you.
Okay. Right. So thank you very much. And if you have any doubt, you can always contact me. You have my email address and everything. So you can, yeah, Santish. So thank you very much. Thank you very much for your support. And it was a great experience for me as well. Now, the thing is, you asked me lots of questions. So I'm quite happy with that, right? So in that manner, I mean, it's comfortable for me as well. So then I think that you are like actively participating in the workshop. So that's a very good thing that I saw in this workshop, right? So very interested to see the enthusiasm in you, right? The passion inside you, right? So I will be we will be uh, organizing future workshops, right? So you can attend to those things, right? And you can contact me if you have any doubt. You have my details, right? So you can always contact me, and I wish you all the best for your future endeavors, and let's meet again. So thank you very much, and have a good night.
Thank you so much.